Hey gang, let's go over the homework problems from the recommended homework exercises from section 5.4. Welcome back to 4600. I should have started with that, as I usually do. So let's kind of get going here with the first exercise was exercise 5.45. So back in exercise 5.1, it was determined that the joint distribution of y sub 1, the number of contracts awarded to firm A, and y sub 2, the number of contracts awarded to firm B, is given by the entries in the following table. So we've got our probability table already set up, which is nice. The marginal probability function of y sub 1 was derived in exercise 5.19 to be binomial with n equals 2 and p equals to 1/3. Are the random variables y sub 1 and y sub 2 independent? And then why are they independent or not? Okay, so it was nice them to give us this table already, so we didn't have to rehash that. So on the next slide, let's do the solution here. So recall that if independent, then p of y sub 1 and y sub 2 must equal p sub 1 of y sub 1 times p sub 2 of y sub 2 for all y sub 1 and y sub 2 combos. Should probably do it like this, or combinations. All right, so whenever I see a table and I've already got my probabilities built out, I'm always going to look at one of the ones with a 0 in it. But you don't have to. Let's take the very first one here and see if the probability of 0 and 0 for y sub 1 and y sub 2 is equal to its marginal probabilities. So that is, let's take the fact that we know p of 0, 0 is equal to 1/9, right? And then if we sum up, if we want to find the marginal probabilities, we've got our marginals. We got p sub 1 of 0 that we're interested in, and that's just the sum of the, my eraser going, it's the sum of this first column here, or when y1 equals 0, so that's going to be 4/9. So that's 4/9. And then we're also interested in the other marginal probability for for y sub 2 when it equals 0, and that's just going to be us summing up the row here, which is also 4/9. So that's 4/9. Can draw a 9 there. But p of 0, 0, 0 and 0 is not equal to p sub 1 of 0 times p sub 2 of 0, because 1/9 is not equal to 4/9 squared, essentially, which is just 16/81, right? So those aren't equal, therefore y sub 1 and y sub 2 are dependent. And I mean, the reason why is because probably should have written this sentence kind of in reverse, but the point will be there. Because p of y sub 1, y sub 2 does not equal p sub 1 of y sub 1, p sub 2 of y sub 2 for all y1 and y2 combinations or combos. Alright, so that's pretty much all there is to that, and we're done with that problem. Alright, so the next problem we had was exercise 5.46, and it asked us to refer to exercise 5.2, the number of heads in 3 coin tosses, which was shown to be binomially distributed, at least the marginals were, with n equals 3 and p equals to 1/2. That's the one where the three balanced coins are tossed independently, and one of the variables of interest, y sub 1, represented the number of heads that were tossed in the three tosses, and y sub 2 denoted the amount of money won on the side bet. And so we've done that problem before, but the question is, are the total number of heads and your winnings on the side bet independent? In other words, is y sub 1 independent of y sub 2? And I went ahead and laid the table out because we've already constructed this before. So refer back to an earlier, to the earlier solution on this if you're not sure where I got this from. I'm pretty sure you probably do at this point. But again, this is the similar situation to the last one, and you can probably already gather that these are going to be dependent, right, on each other. Because it does kind of make sense if you just think about it from a logical standpoint that obviously the amount of money you win depends on the number of heads you toss, right? So that seems like probabilistically that should work out as well to show us that these things depend on each other, or that the two random variables do. So again, I'm just writing this for reference. Independent, I'll just do I and D here. If P of y sub 1, y sub 2 equals the marginals multiplied together for all combos. I'll shorten it there for us. Okay. So I'm going to just take any one that I want here. If I took the first one here, I'm probably going to assume that that's probably that looks like it would be independent, because the row total, well, actually it wouldn't be, because the row total and the column total are both 1/8. So if you did 0, -1 as your combination, you would also find that these aren't independent. But the one I chose, and I kind of go with pick one of the ones that are 0, so where the probability is 0, that is. So I picked when y1 equals 3, y2 equals 3. So let's take P of 3, 3 equal to 0. Again, you can take any of these combinations and see if it works out, but you only need to find one that doesn't work out to show that the random variables are dependent. And then the marginals here for P sub 1 of 3 is going to be the row total or the column total here, which is 1/8. Right, and then the marginal for y sub 2 when it equals 3 is going to be also the row total for when y sub 2 equals 3, which is this row here. So that's also 1/8. So we get 1/8 there. And then of course we can just show it through the rest of the process. P of 3 and 3 does not equal P sub 1 of 3, P sub 2 of 3. You could probably leave this here if you've shown me this stuff here already. That's probably fine. I just like to write in the numbers just to kind of drive the point home, to be more official, I guess. That's 1/8 over 1/8, and we know that's 1 over 64. So those aren't equivalent, thus y1 and y sub 2 are dependent. Alright, so that's all there is to that problem. It's kind of nice when you've got a table like this where you don't have to show it's true for all cases, like the one we did in the actual lecture on the rolling of the die. It's very rare that an entire discrete population will be independent, but they do occur, as we saw with the die rolling. But when you start adding different stipulations, like the money amount matters based on the heads in this case, then it's probably going to be dependent, to be honest with you, in situations like that. Okay, so that's the end of that one. We'll move on to the next. Okay. The next exercise was exercise 5.50, and it's a continuous variety here. It says in exercises 5.6, we assumed that if a radioactive particle is randomly located in a square with sides of unit length, a reasonable model for the joint density function for y sub 1 and y sub 2 is given by the following. And part A just asked, are y sub 1 and y sub 2 independent? And it says, does the result from part A explain the results you obtained back in exercise 5.24? Answers D through F. And why? We'll have to look back at that one and see if, I'm not really so concerned with this part of the problem. I'm more concerned with this part of the problem here. So part A is really what I want to go over here. But let's see what happens with this problem, and whether that functions actually, the two random variables are independent or not. Okay. And so this is going to be a nice little, this is going to be our typical little, everything, y sub 1 is between 0 and 1, y sub 2 is between 0 and 1, and so we end up getting, our regular square, and our region we're interested in is that. So this is a pretty simple one to get the marginal probabilities for, and that's what we have to start with, right? And that equals the integral from 0 to 1 of 1 dy sub 2 with respect to y2, which just ends up being y sub 2 integrated from 0 to 1, which is just 1 for 0 less than or equal to y sub 1 less than or equal to 1. And the marginal for y sub 2 is going to be the integral, and it's going to go from 0 to 1 as well, of 1, but with respect to y sub 1, and really we're going to get the same thing in this case, because this is a nice, basically a uniform bivariate distribution. Y sub 2 is less than or equal to 1, so we got those two guys. So it looks to me like these are going to be independent for sure. Just show me by doing the following. Say that the f of y sub 1, y sub 2 has to equal to the marginal times the marginal of the second, and that's just 1 equals 1 times 1, which that's true all day long. So y1 and y sub 2 are independent. So that one was pretty simple. Now, as far as part B, what it's asking there, let's see if I can go back and find that exercise 5.24, specifically answer C. Let's see if we did that one. I'm trying to remember if we did that one or not. 5.24 C through, what was it? C through, or D, E, and F. The answers for D, E, and F. In fact, I don't think we did that one, that particular one. Let me see if I can muster up the book here. Let's see. Let's pull this over here. Let's go back to exercise 5.24 right here. So D through F, D, E, and F, and it said for any y sub 2 between 0 and 1, what is the conditional density function of y sub 1 given y sub 2 equals y sub 2? I'd be willing to bet the answer to that was 1. And so it probably wouldn't have surprised us there if we had done that problem. In E and F, the probabilities that y1 was between 0.3 and 0.5, given that y sub 2 equals 0.3. Let's just see what the answers to those were so we can kind of figure out what that second part of that question's asking. So it's 5.24. Let's take a look at it. We'll cheat a little bit here because since we didn't solve that problem, we'll see what the solutions for D, E, and F were and see if we're surprised by them, apparently. D was f of y sub 1 given y sub 2. F of y sub 1 ended up equaling 1 in this case, which is not a surprise. That's what we just found that the marginal probability distribution was. And also E and F both gave us the same probabilities regardless of what we held y sub 2 to, because Being independent means that we should have gotten the same solution no matter what value we chose for y sub 2, because these variables aren't dependent on one another. And so if you just go over the same range here, what value you pick for y sub 2 to be the given in these cases doesn't matter to us when it's independent, because if you recall, if it's true that, going back to the basic probability rules, if it's true that probability, remember a conditional probability, like say A given B is equal to the AND of the two events, divided by the probability of the given, right? So, and when probabilities are independent, that basic formula is the probability of A times the probability of B, right? And so if we were to solve this thing for the probability of A in this case, then we get probability of A is equal to the probability of A and B divided by the probability of B, right? Therefore, if two things are independent, it doesn't matter what the given is, they still equal the probability A if they're independent. And so that's why it's really not a shocker here, okay? So the answers that we just saw from 5.24 for those three things, part E and F, the reason we got the same probability is because the intervals over which we're looking are both between 0 and 1, and the function, the marginal functions are both 1 no matter what we do, right? And so we're going to get the same probability either way, being that this is independent. And apparently that's something that does happen quite often with when we have two random variables that are independent of each other. One doesn't rely on the other, so therefore the probabilities only rely on one variable or the other separately when you're looking at those things. And so that's what's going on with that part of that question. Okay, so that's just an add-on there, just some extra information. Part A was really what I was more interested in going over with you anyway. Okay, let's move on to the next one, which is exercise 5.52. So this is probably familiar looking our joint probability distribution function for y sub 1, y sub 2, where y sub 1 is between 0, 1, and y sub 2 is between 0, 1, and 0 elsewhere. And then they're just simply asking, are y sub 1 and y sub 2 independent? We're going to use, I'm going to invoke theorem 5.5 here because we can get away with it. So from theorem 5.5, notice that for y sub 1, y sub 2 is something is all multiplied together, that term is, and so we can break it apart and separate the y sub 1 and y sub 2 into two different pieces. And it's also because these guys are separated out here as well, so we can get away with this. So recall that theorem 5.5 is the one that says that f of y sub 1 and y sub 2, that those two random variables are independent if we can rewrite this as a combination or a multiple of g of y sub 1 times h of y sub 2. Okay. And so from theorem 5.5, g of y sub 1, all right, is going to be equal to the function, let's separate this up and call it 2y sub 1 for 0 less than or equal to y sub 1 less than or equal to 1 and 0 otherwise. And g of y sub 2 equal to 2y sub 2 for when y2 is between and equal to 0 or 1 and 0 otherwise. Okay, so thus we know that these two things are going to be equivalent. That is that 4y sub 1 times y sub 2 is equal to 2y sub 1 times 2y sub 2, which does equal indeed 4y sub 1 y sub 2. So this one was kind of simple and not too bad. If you invoke theorem 5.5, it was even easier, or a little shorter work anyway. I think even if you did find the marginals, you would have come to the same conclusion anyway. As a matter of fact, we would have probably gotten these guys as our marginals. Had we done the integral for each one. So y sub 1 and y sub 2 are independent. And that is all there is to that one, folks. We'll move on to the next one. Okay, so the next one is exercise 5.53. This also should look like a kind of familiar function we've seen before. This is the one where we had to find k in exercise 5.9 to satisfy this PDF, essentially. And so we're again trying to showcase that this is that these are independent. I'm not going to try to do these on the same slide. Feel free to do so if you want. I just don't want to draw that small. So I'm going to go to the next slide to do my solutions. So down here I'm going to sketch my image of that space, and I want you to note something real quick before we move on. Note that we are already probably going to assume that these the two random variables do depend on each other based on this. So this tells me when I see that y sub 1 and y sub 2 are in the same inequality that I cannot use theorem 5.5. Right, so in this case. All right. But we do need to make sure that we pay attention that y sub 1 has to be less than or equal to y sub 2, because that's going to help us with our image as usual. All right, so y sub 1, y sub 2, let's say 1 and 1, and that y sub 1 less than or equal to y sub 2 is going to make us draw this diagonal line with a slope of 1. And when is y sub 1 less than or equal to y sub 2? It's up in this upper tier here. So that's going to help us find our joints, our marginal probability functions for this distribution. So for a little f of sub 1 of y sub 1, I got to integrate the function 6 minus 6y sub 2 dy sub 2 from in the y2 direction. So from the line up to 1, and so I'm going to go from y sub 1 up to 1 there, and we just integrate the sucker out. So integrating with respect to y sub 2, we get 6y sub 2 minus 3y sub 2 squared from y sub 1 to 1, which is going to equal, plugging in 1 into both of those gives me 6 minus 3, so that's just going to be 3 minus, plugging in y sub 1, we get 6y sub 1 plus 3y sub 1 squared, which recall we did this before already. That's 3 times 1 minus y sub 1 quantity squared when we clean it up for 0 less than or equal to y sub 1 less than or equal to 1. And there's our marginal probability function for y sub 1. Y sub 2 is going to be the integral of the same thing, 6 minus 6y sub 2 with respect to y sub 1. And this time we're going from 0 out to the line of y sub 2. All right. And that one's going to equal 6y sub 1 minus 6y sub 1, 6y sub 1 times y sub 2 from 0 to y sub 2. So we end up getting 6y sub 2 minus 6y sub 2 squared, which just equals 6y sub 2 times 1 minus y sub 2 from 0 less than or equal to y sub 2 less than or equal to 1. And we got our marginal probability distribution. All right. Obviously, this is going to be dependent, right? We kind of knew that from the get-go. But again, we got to show it. So we're going to. Thus, f of y sub 1 comma y sub 2 does not equal the marginal probabilities for y sub 1 times the marginal probability of y sub 2. because 6 of 1 minus y sub 2, which is the original function on the previous slide, does not equal 3 times 1 minus y sub 1 squared times 6y sub 2 times 1 minus y sub 2. There's no way that's going to multiply together, and I wouldn't even clean that up. To be honest with you, it's pretty obvious those aren't going to be the same at all. So obviously the random variables y sub 1 and y sub 2 are dependent, and we've shown it. Okay, and that's it to that one. So not too bad. It's just a matter of finding the marginals again and doing what we did. Okay, let's do the last example, 5.60. This is not a problem we've done before, or I should say a joint probability function we've worked with before. But apparently in exercise 516, the two random variables denoted the proportions of time that employees 1 and employees 1 and 2 actually spent working on their assigned tasks during a workday. So the joint probability is given to us is the following, and it just says simply the same thing we've been asking all along: are the random variables actually independent of each other? Now you will note that these guys are separated out, and you might want to first, when you see that, get excited and go, "Oh, we can just use theorem 5.5," but you can't here. And the reason why is because we can't separate y sub 1 plus y sub 2 because those things aren't multiplied together. We have to be able to separate it into two things where y sub 1 and y sub 2 can totally be separated, but when multiplied back together give me the same thing. That's going to be a tall task here, so we're going to have to revert to just finding our marginals and proving whether these are independent or not that way. And so both of the things are between 0 and 1. I don't really have to worry about the limits of integration here because they're going to be between 0 and 1 no matter what, and I'm not trying to find a probability. But again, it's always good craftsmanship or good mathematicianship, if you will, to draw your image regardless, and just to kind of show that you get comfortable with a shaded area. And so we need to commence defining the marginals for that function first. So we need to find the marginal for y sub 1, which is going to be the integral from 0 to 1 of y sub 1 plus y sub 2 integrated with respect to the y sub 2 variable. That's going to end up giving me y sub 1 times y sub 2 plus 1/2 y sub 2 squared, evaluated from 0 to 1, which just ends up being y sub 1 plus 1/2 for 0 less than or equal to y sub 1 less than or equal to 1. So there's the marginal for y sub 1. Y sub 2 is marginal function. Again, we're going in the y sub 1 direction this time, and it's going from 0 to 1 with the same function, y sub 1 plus y sub 2. All right. And when we do that with respect to y sub 1, we get 1/2 y sub 1 squared plus y sub 1 times y sub 2 from 0 to 1. And now that gives me 1/2 plus y sub 2. All right, for 0 less than or equal to y sub 2 less than or equal to 1. Are paying attention to the marginal distributions, like kind of regions, important here? I haven't really said a whole lot about that or how I felt about that. It does. It means that you know what, if you had to further integrate this now with respect to y2, because we did it already with the opposite variable, or y1, like for example, in the first function, marginal, we already integrated with respect to y2. We can still integrate this new integral to answer questions with respect to y1, as we saw when we had to do some things with conditional probabilities in 5.3. So it is important that we remind ourselves where that function resides. All right, and a lot of times it does come back to the original limits that were on the original function, as i.e. these guys here. But sometimes we've seen them change depending on the way our results came out, right? So we have to kind of keep abreast of those things as we go through. It's important. Okay, so we've got that information, and I would say the following. Thus, little f of y sub 1, y sub 2 does not equal f sub 1 of y sub 1. You might not know it until you plug it all together and investigate what f sub 2, y sub 2. Because y sub 1 plus y sub 2, the original function, there's no way it's going to equal the marginals multiplied together. Y sub 1 plus 1/2 times 1/2 plus y sub 2. There's no way if we FOIL that sucker out it's going to be the same. They're not equal. Therefore, again, y sub 1 and y sub 2 are dependent. Honestly, that's why it's important to probably do the marginals and then multiply them together to see if you get back to the original function and not always rely on that theorem 5.5. That was kind of the point I kind of hinted on or said something about in the previous lecture, about that we can't always rely on 5.5, and this is a good example of why we can't always rely on it. We can't just split that apart. Now, you can't assume until we did what we did that they're not that they're dependent or independent. You can't assume one way or the other without doing the investigation first. So it's always important to do that. But that is it for the recommended homework solutions. And if you got any questions, please let me know. Take care, guys.